Okay, it's already 4:32. It's our pleasure to be here again and to introduce Professor Thomas Gabor. I don't know if I'm speaking your surname correctly, but anyway, you can correct me if I'm wrong. I just want to give an introduction to say to everyone that is watching us that this series of talks, QCTalks, is an initiative of the University of Porto, particularly from people from Faculty of Engineering, but joining some other people from other departments to promote and disseminate quantum computing. And we have been inviting people to talk, and we have this series of talks. And today we have the pleasure of having here with us Professor Thomas Gabor. Thomas looks a bit young, but he has an extensive path here. His curriculum is very impressive. So besides having interest in quantum computing and quantum artificial intelligence, he also works in artificial intelligence. He has interest for some subjects that are very interesting, like artificial life or evolutionary algorithms. So I'm sure that you'll be delighted with his talk. So the floor is yours, Thomas, please. Thank you very much.
All right. Thank you for the introduction. Just to clarify, I'm not a professor yet, but I just get right into the matter of things. All right, so I have this talk today with me. It's called Towards Quantum Artificial Intelligence, and as you found out, I also have a background besides quantum computing, coming from more traditional artificial intelligence topics and topics in optimization. And this is kind of what will shape our journey today, coming from the classical world into the quantum world in that matter. So for the, I guess, quantum computing audience, I thought the thing we should start with is, just get me focused. Yes, the question, what even is artificial intelligence? So I think everyone involved in computer sciences has come to meet artificial intelligence in some way or the other, has gotten ways to use artificial intelligence. But just so that we start with a common understanding of the technology, I've prepared a very basic image of what we are gonna use as a foundational knowledge of artificial intelligence. And throughout the ages, I've compared this very simple slide of how everything in machine learning basically kind of works. So just to get through the phases we see here is usually when we perform some process of machine learning, what we want as an artifact is some kind of decision model. This can be a decision tree, for example, or some function. Usually today it's a neural network that's behind this decision model. And without any knowledge about what kind of decision model we want for our problem, we start with random initialization, just start with anything. And then we have this iterative loop right here. That's the middle of this chart. And that's iterated many times to just improve on the decision model. And with every iteration, hopefully our decision model gets better until it fulfills some kind of criterion where we say, okay, it's done, we can stop. The way we can see how good the decision model is by executing it, just running it in the wild, having it try to do something that we expect it to do, that we trained it for originally. And this is where we come up with some sort of result. If the result is good for us, we can just output it and be done with the whole process. If the result is not yet what we expect from our decision model, then we continue with another iteration. And this iteration is usually triggered by some kind of reward or loss. So we need some metric to tell the machine how good our decision model is to our liking, is in our perspective. And given that reward or loss function, artificial intelligence can then perform an update to generate another decision model that's hopefully better with respect to that reward or loss function. So this is the basic understanding of machine learning that I'm going to use here, just as a very basic process. Of course, as I said, we have worked in machine learning itself as well. Here's actually the same model, a bit more complicated. This is what happens when you develop a machine learning model in industry cooperation. This one stems from a long ongoing cooperation with Siemens, which is just a bit more technical, a bit more fleshed out on the artifacts that are used. But what it encapsulates, even in this complex form, is basically just a process like this, which iteratively gets better from random initialization through basically just random executions of formally random results and going on and on about that. So this is what I mean when I talk about machine learning, just so we're clear on that page. And now I like to motivate our research into quantum AI by a simple observation made about artificial intelligence on its own. And perhaps it's not so simple. It was made like 2 years ago right now by Rich Sutton. And for those who don't know, Rich Sutton is like one of the founding fathers of modern artificial intelligence. He's often introduced as the guy who wrote the book on reinforcement learning. So he's one of the big names in the field of artificial intelligence. And he had this very interesting blog post, as I said, I think 2 years back. He called The Bitter Lesson. And it just sums up his experience with decades of research in artificial intelligence. And I just brought with me few observations he made. And he sums up these 4 observations, actually, just in that order, where he says, there's one process that always happens in AI research. And he says it starts with AI researchers often try to build knowledge into their agents. So they have some kind of machine learning model that works, that learns something about most domains, and they want to solve a specific problem. And usually, if you know more about the problem than the machine, then you can make the machine better by just building your knowledge into the machine. So AI researchers tend to do that, build additional knowledge into the agents. And because originally you know more about the problem than the machine, this always helps in the short term. And as he adds, it is personally satisfying to the researcher because the results improve at first. But, and this is the bitter observation, I think, in the long run, this process plateaus and it even inhibits further progress because we reach that point where the machine is just as good as you are in that domain, and then you cannot improve the machine by putting in further more of your knowledge because you just run out of your knowledge. And so this is when kind of the research progress comes to a quick standstill. And in the past, what's happened then is that another breakthrough comes along. And usually this breakthrough is not achieved by adding more knowledge about the problem, but just by adding more computation to the solution. So finding a new way to let the machine do more of the thinking. And as I said, that's when breakthrough progress happens via an opposing approach based on scaling computation by search and learning. So what he kind of advocates in this blog post is, and there's sums up the biggest lesson that can be read from 70 years of AI research, is that general methods that leverage computation are ultimately the most effective and by a large margin. So I think it's very nicely and very compactly summed up that what AI is going for. We don't want to program it by hand. When we talk about AI, you want to leverage computation on a large scale, and we want to have AI reinvent our knowledge automatically, basically. So this sounds very nice. If we take this lesson for granted, then we should never apply our own knowledge, just let the machine do all the computing, do all the work, do all the thinking. Of course, there's an issue with that, using too much compute, because that's exactly what has happened in the recent years. This is another interesting blog post that goes nicely along together. Also, I don't think they are connected in any way. This is by a team at Google, and they analyzed the machine learning breakthroughs that have happened in the recent years. You can see on this plot, they have been analyzing since 2012 what the big machine learning breakthroughs were. And they just plotted how much computational power went into these singular breakthroughs. And they plotted this, as you see here, on an exponential scale. So the takeaway here is that whenever a new experiment came along in the last years that granted a new breakthrough idea in machine learning or artificial intelligence, it was always achieved by putting in exponentially more computation power into solving such a problem. And again, in this blog post, they sum up what they are talking about. Since 2012, the amount of compute used in the largest AI training runs has been increasing exponentially by a 3.5-month doubling time. And just for comparison, Moore's law usually is given with an 18-month doubling period. So this is how the hardware increase. And this just shows that current AI experiments outgrow hardware growth by a large margin. So the amount of compute necessary to do something exceptional outgrows the available hardware by a large margin right now. So just with simple extrapolation, a little bit of math, we can clearly see where this leads us to. And at first, it's a grim future. So the obvious options are this process cannot go along forever. So we cannot outgrow the hardware growth for infinite time. Someday we will just need to use every available computer on Earth to do an AI experiment, and then kind of we're done with AI experiments for a while. So the possible options are just that maybe progress in AI research just needs to slow down. So adapt to the hardware growth we have, the growth in available computational power, and just become slower in that way. Of course, for a while, we can compensate that process by putting in exponentially more money, because as long as there's still hardware to buy, we can just compensate for the slower hardware growth by buying even more and more hardware. And of course, this process also runs out of resources at some point. We cannot put in infinitely much money. And more interesting options as scientists for you, perhaps, we could develop new AI algorithms that are much more resource efficient. And what's maybe the best for everyone basically is we could tap into new sources of computational power if we find those. So I think you see where this is going. But first of all, there are, of course, we're not the only ones in this session realizing these problems. So there is some research going into this. And first of all, people have been looking at more resource efficient AI algorithms, which I just want to mention really quickly. Actually, it's basically by the same team at Google. A few years later, they did another study on computational power in AI, and they found that actually for every experiment that has been done with large resources, they have always been found at the later moment in time more efficient representations. So you can then, when you know how to do it, you can often make these experiments more efficient. They said compared to 2012, it now takes 44 times less compute to train a neural network to the level of AlexNet. By contrast, Moore's law would yield an 11 times cost improvement over this period. Our research suggests that for AI tasks with high levels of recent investment, algorithmic process has yielded more gains than classical hardware efficiency. So we are outgrowing hardware efficiency just by inventing new algorithms. But as you also notice, the factor here is still not as large as the factor we've seen in the graph before. So this is very nice, and this is definitely an interesting line to go for, an interesting line of research. We should still have a look at the last point here where we say, okay, what about new sources of computational power? And in the recent years, so when I first talked about this issue there, this directly led to quantum computing, as you may imagine. For this talk right now, I think we go to one more slide where we consider the classical approaches to new computational power, because these are very active right now and just in the recent years, I'd say. So if you look back at our model, we see mostly 2 points within this model where classical hardware developers have gone and developed specialized approaches to improve performance. What is probably most well known is here in the update part, that updates along big neural networks mostly are very expensive, and that people have found out a few years ago that graphics cards can do exactly those computations that help that are necessary, and such graphic cards can be used to improve performance when learning a neural network. Right now, this has become such an important task that other specialized hardware is developed. There are designated cards just for training neural networks that you can put in your computer. And even recent machines, like I think mostly Apple computers, actually design specialized chips for neural network processing within their standard CPU. And yeah, so there's been some specialized hardware here. On the other side, we have the execution test. So when I have a very complex neural network, for example, a very complex decision model, usually want to apply it fast so I can improve my performance in practice. And also here you can find a few approaches. I think the most interesting one in the recent years is something called the neural compute stick. It's a small USB stick that you can mostly integrate with factory hardware or factory control computers. And it just augments the ability of such computers to execute neural networks. So if you have a well-trained neural network for, let's say, anomaly detection in a product line, you can just put in this USB stick and upgrade your production line with the ability to use very fast neural networks for this task. And this is very nice. And then we've seen some improvements on the software side as well, which I find very interesting, where you can improve training via by using not like data grounded in the real world, by using more and more data that you can generate along the process, which just improves the overall pipeline performance, I'd say. So we have simulation software going to digital twins and stuff like that to use for extensive simulations. These are, of course, very costly to compute. So they are not, a digital twin in itself is not accelerating anything, but it's still faster than like gathering data from the real world. So this is kind of where people try to get a little bit faster here, and generative learning goes into that direction. What I find very interesting, I made a point like this, I think about a year ago when we spoke to Infineon. And they all nodded heads. Infineon is in this business of developing these specialized chips. And then even they told me, yeah, it's very nice what we do, but on the long run, we cannot solve the problem with these chips. So as long as we're using the hardware we know, there's a limit to how much improvement we are expected to get performance-wise. So after all this, of course, what this storyline leads into is, well, we are within a series of talks where we've done nothing but talk about new computational resources. And so maybe this is the point where we can aid the development of artificial intelligence by using quantum computing. And as you can see in this picture, quantum computing is kind of represented by the more reddish tone. So we can look for non-classical approaches here, maybe to help artificial intelligence along. All right. So this is kind of the motivation of why we should care about quantum AI, why exactly bring quantum into this. Just give me a moment. Of course, we've seen that we would use any kind of computational resource, and this is just the one that seems most promising right now. I think there are a few better reasons, though, and I'd like to talk about them because I think they are severely underrepresented in the discussion of this field. And there are some, I think, very intriguing matches between what quantum computing does and what artificial intelligence needs, and actually vice versa. So we've already talked about how the main goal of quantum computing is to provide more computational power in some way or the other. And as we've also seen now, artificial intelligence is a field that is always in dire need for more computational power. I've also seen a few additional interesting connections. For example, that we're talking a lot about how we can cope with noisiness in quantum computing, which right now, of course, is for many applications like many factors above what we can actually use for practical algorithms. But coming from artificial intelligence, machine learning in general, I think it's a very interesting observation that all of these algorithms we use in that field desperately need randomness. So what I'm doing on a classical machine is I'm trying to get by I try to gather entropy from some sources to have a randomized search process run. And So yeah, I jumped through a few hoops to just generate randomness that maybe a noisy quantum computer could give me for free. And second, because these algorithms usually thrive in a very randomized environment, they're also very, very robust to noisy processes. So if I do a machine learning upgrade and it goes entirely wrong because of noise, I can also correct it very easily. So these are very robust algorithms that actually need randomness to some extent, at least. Of course, there's still a large gap between the non-randomness we get from quantum computing and the randomness that artificial intelligence actually need. But maybe this is an application where we can close that gap earlier than in more deterministic goal functions, let's say. Then, and this is what we're mostly be getting into for the rest of the talk, I think, is that quantum computing offers multiple approaches to perform stochastic search. We'll talk a lot about quantum annealing shortly. QAR is also a very popular approach. And stochastic search is actually one of the main processes used in artificial intelligence, one of the main processes used for that update bubble that we've seen earlier. And then maybe just as a bit of an outlook, we won't be talking about this today, is that I think as we've also seen in the last few talks in this series is that quantum algorithms can be very hard to construct. First, just to construct them with the hardware we have at hand. If I know how they are supposed to run, just translating them to what I have in practice. And then it's also probably much harder to just invent new algorithms. So we're not at that point yet in quantum computing where I can say, hey, I have this completely new problem. What could a quantum algorithm look like? We just have a few quantum algorithms in our toolbox and we need to work with those few algorithms. It's very hard to just sketch something from scratch, basically. And this often looks like a very interesting machine learning problem if we want to go the other way around. As I said, perhaps just take this as inspiration. We're nowhere near doing anything on that in that direction. So what both approaches have in common here, and I think this is why we have all these matches in how they actually work, is that both operate on a multitude of possibilities, need large amounts of compute to return a relatively short answer. So this is what we can perhaps use. And it's very interesting. I'll be talking about this a little bit more later, that in Germany we have this pretty big project on quantum artificial intelligence that's led by Frank Leimand, who's also given a talk in this series already. And as part of this, we've started with making a quick survey of what in quantum AI algorithms you already know of. And there are quite a lot. So we're not like the first identifying that this is an important field. There are quite a lot of approaches. And you can see a short overview here. I also put in the reference to the paper where you can see this explained. So we have some kind of survey type of research going into that. In the end, you can use all of this knowledge. You can access it easily via the Planck platform when the Planck platform is finally ready. So this will just take a little bit longer. The paper is out there right now. But just to put it very quickly, when you consider these quantum AI approaches that already exist, we can see how they target specific phases of this whole loop to improve them via quantum algorithms in some way or the other. And looking at this model, as I said, I just want to get into a few specific points. And you remember that when we've looked at what the classical hardware tries to improve with specialized hardware, we've seen that this is mainly the update bubble and the execution bubble, maybe. So I think this is the approaches that we're gonna look at right now. And we'll start with the update bubble. And as I already mentioned, one of the central ways of solving an optimization problem, doing such an optimization update, basically, using quantum technologies is quantum annealing. And I think as we didn't have very much information about quantum annealing yet in this series, I thought I'd just give a quick rundown of what is quantum annealing and how do we look at it. And here for the most basic slide, quantum annealing, first of all, is an algorithm developed in 1998, and then a bit later in 2011, first implemented by D-Wave systems. And quantum annealing, as it is done by D-Wave systems, as it is done in practice, basically runs on specialized hardware. This is not a traditional gate model quantum computer. There aren't any gates at all. It's specialized hardware just for solving quantum annealing optimization. It's using quantum-ish effects, let's say. There has been an ongoing discussion in the quantum community, which you've probably heard of, if these D-Wave machines usually actually profit that much from quantum effects, so if it's other effects at work. I must say I'm kind of neutral on that discussion. I'm not a physicist. I cannot evaluate the physics behind this, but I'm a computer scientist, and we can look at how to use these machines, how to use them right now, and perhaps how to use more quantum annealer in the future, because the theoretical algorithm is well known and we know how it works, and we can evaluate that right now. And as I already said, the ultimate goal of quantum annealing is always to solve an optimization problem. So just to give a quick impression of how this works, this is actually, as of now, the last generation D-Wave chip, and just a smaller excerpt of it, of the architecture that such a quantum annealing device uses. And as you can probably think, the little nodes here on that graph are qubits, and the edges of that graph are connections between two qubits. So as you already see, not all qubits are connected, as is pretty common for quantum machines right now. And we have this kind of pattern of connected qubits, and we can use them for optimization. So how does this work? This is basically the quick summary of how quantum annealing works. So we can apply something called field strength to every qubit. It's just a bias that says, okay, if there's a specific qubit we expect to be set in our solution, then we can give it a bias to be that way. Usually we need to set some biases to actually motivate the quantum annealer to do anything and not just to turn an entirely trivial zero solution. What's more interesting is we can add something called coupling strength to couples of qubits. So on every one of these edges, they connect two qubits, and we can basically define a dependency between these two qubits. We can tell the quantum annealer, hey, if this qubit 1 is set to 1, then this other qubit probably should be set to 1 as well. Or we can tell the quantum annealer, if this is set to 1, this other qubit should probably be set to 0. And this is basically this is the whole language we have to express our optimization problems. As we'll see later, this is entirely enough to express most optimization problems we meet in practice. And once we have expressed our problem in that way, what basically the machine does, so in this case, the physical universe always tries to minimize the energy of a given system. And so we can trick it into finding the qubit configuration that has overall the lowest energy for the entire system. And if we set our field strength and coupling strength the right way, then the qubit configuration that has the lowest energy for this qubit machine will also represent information about the solution to a given optimization problem that we want to solve. Not lowest energy for a quantum annealer, but something else that we have then translated to lowest energy for a quantum annealer. And as is common with quantum algorithms, this minimization of total energy, and this is the part where the universe, let's say, usually uses some kind of quantum effects. If it does, I thought about the ongoing debate there. But let's assume it does, then at some point when this kind of computation is done, when the algorithm is run, what we need to do, of course, is measure a result. At this point, all we're getting back is common classical bits. And at this point, yeah, the qubits have assumed one configuration, 0 or 1 per qubit, and all of them together form a state that usually represents the minimum for the total energy of the system. So to just get into this in a bit more detail, Here we just have like a zoom in picture with just 6 qubits within this grid, and we can just give another quick rundown through the whole algorithm. So first we can apply field strength. Let's say for this qubit here on the bottom left, we say we want a positive field strength. This means that means if this qubit is set to 1, it will contribute positively to the overall system's energy. So positive field strength usually motivates the quantum annealer to set this qubit to 0. But it doesn't have to. It may pay off to actually set it to 1, acquire the additional energy to get lower energy values on other qubits. So as I said, the next step is that we need to define some connections between these qubits. We could have a negative connection between these 2 qubits, which would then say, okay, if this bottom qubit is 1, then the above qubit should be the opposite. So we have some kind of we give some hints into what a good solution would look like this way. And of course, as you've seen in the graph, we have not only the option to put like singular connections. These qubits, albeit not fully connected, have a lot of connections between each other in this given pattern, and usually have connections to others of these cells along the way of the grid. So there are lots of these connections that we can build up and use for our computation. And then what happens in the theoretical algorithm called adiabatic quantum computing is that in theory, we could add these constraints infinitely slowly, and then by this doing so without adding any energy to the system. And as the system cannot gain more energy this way, it needs to remain in the lowest energy state possible, and this would be our solution. So if this works perfectly, adiabatic quantum computing can, for optimization problems formulated in this manner, practically jump directly to the global optimal solution without going through all the errors and mistakes that a classical algorithm needs to make at this point. Of course, doing something infinitely slowly with adding no energy is not really that possible in our physical universe. So what practical quantum annealing does is it just tries to do this process quite slowly and with almost no energy. And this is where we get a lot of noise from. And as always with quantum computing technologies, we don't get perfect results this way, but instead we get noisy results with a kind of error. And then in the end, if we measure this, all these qubits jump to a specific result. We can just read out a result vector and map this back to our problem specification, and we have a result of the quantum annealing computation. Mathematically, this is basically what we do. It's a very simple formula. As you can see, we minimize result vector made out of these qubits, which are in the end 0 or 1. And then we just sum over possible multiples of these various qubits. And what comes in there is a factor, and that is basically given by our constraints and this field variable. And we can write these factors just in one single upper triangle matrix called W for our case. We can see a lot of these matrices shortly. We'll just give one quick example of how this whole translation to a quantum annealing process works. And of course, this formulation is called quadratic unconstrained binary optimization. It exists in a realm of theoretical computer science completely independent of quantum computing as well. And it's known to be NP complete. So this is very interesting because, of course, there are very interesting problems that are NP complete that can all be mapped onto QAR this way. All right, so just as a quick example, one of these interesting problems is graph coloring, which probably many people know from basic courses. We are given a connected graph, we are given a set of colors, and we want to get a colored graph that, such a way that no neighboring nodes have the same color. And this is pretty easy to do for small examples. We'll do it on a quantum annealer right now for even a smaller example. Let's take just the smallest connected graph you can get, basically with 3 nodes and 3 edges. We have a set of colors of 3 colors. We need to color it in that way that every node has a different color, and we can encode this result using the vectors, the bit vector here written below that example. And this we can now translate into a QAR formulation. And we don't need to look into the details here. You can see the mathematical formulation at the top. Again, this is the result we want at the top right. And interesting, just so you can have an imagination how this works, what we end up with when we encode the problem is this matrix here at the bottom left. This is our W matrix. Here are all the constraints on the graph edges, and all the constraints on the single qubits are encoded. And this is what we put onto the quantum annealer. Empty cells are just zeros. And so we end up with such an upper triangle matrix, and this encodes our single problem instance. And of course, if we actually program this, we write it in Python and throw it onto some solver machine and go for it.
Thomas,
all right.
Can I interrupt just a second because someone wants to ask a question?
Yes, sure.
Yeah, Nahid, she wants to ask about the coherence effects and about the interaction between qubits in the model described, in the model that you described earlier.
Yes. Yeah, so to get a bit into a bit more detail, just in theory, if you look at this, let's say here at this point, neighboring qubits should be entangled to some point. As I said, it's D-Wave system says that this is completely a quantum effect. It works perfectly. This is quantum entanglement. There has been some ongoing debate to say, well, we don't know exactly how long the decoherence times are, and if what we measure in the end is still that much quantum. But in theory, what should happen is that we enter a superposition of basically all possible solution vectors on these qubits. And we start with a known global optimum for a known problem, and then we kind of shift from that problem to the constraints that we actually want to solve. And when we do this without any adding any energy, then the whole system needs to remain in the ground state because it cannot jump to a higher energy state, basically. This is as much as I get from the kind of physics side of you. So to cut it short, basically just is that, yeah, for the theoretical algorithm, all of this constraint adding, as I named it, should be in a state of quantum entanglement. But we're not. I cannot guarantee you that the coherence times on current machines are actually long enough to guarantee that. Is this all right?
Yeah, I think so. Yeah, she's saying thank you very much. Maybe she will ask you questions later. If we have time, I'll put her to talk to you. Okay.
All right. Yes, of course.
All right. Thank you very much.
All right. I just got on then. Yeah. You noticed the perfect point to ask a question, because now we're getting into the next section. So now that we've introduced quantum annealing shortly, what can we do with it? And I just want to run down a few examples. And again, if we have a look at this one chart, we will start with the update bubble. So we can see, okay, if we use quantum annealing as suggested here to update models, what models can we update? How does this look like? And I'd like to start with a very nice paper I can only recommend by friends at the Jülich Supercomputing Center in Germany. And they have given a very in-depth explanation on how to train a support vector machine on a quantum annealer. For the details, of course, you just need to look into the paper. What happens is the same that we did for our graph calling problem. They take the problem of optimizing a support vector machine, translate it to a QAR formulation, which is a bit more complicated than for our graph problem. And then they just apply it, and they can train support vector machines. As you can see here on the top left, they have their benchmark, the classical support vector machine, as solved by a classical algorithm. And then they have various outputs due to noise from a quantum annealing support vector machine. And what the colors indicate here is that it's not as sure in what it's actually doing in the result than the classical version was for this very simple problem. But we can, I think, still recognize that it actually works as a support vector machine. So it recognizes the clusters as we would expect it to do. So this is an approach where we can use quantum annealing to train support vector machines. As with most things in quantum computing, you probably know, I wouldn't expect any of these techniques right now to offer a practical advantage, but I think it's an interesting direction to go for. And of course, if the machines grow in size, grow in capability, one day this may be very important as a use case. All right. So just as a reading recommendation, aside from our own papers, now let's get into our own papers. What we did is, as you can see, a very similar study, for example, for archetypal analysis. So it's a problem where you can see a set of data points, and in this case, you want to pick out 3 so-called archetypes that represent the extremes of the data point. And as you can see, how good archetypes are is often measured by how much area they cover within this entire data set. And here we can see the state-of-the-art R package archetypes that for this data set decides on these 3. It's the corner nodes of this triangle. These are chosen as archetypes to represent the whole data set in its archetypes, basically. It's not the average, just the most typical, most pure representations, let's say. And we can see on the right that the approach, the solutions that our quantum annealing based approach here generates are actually quite similar. So again, don't expect an actual performance increase right now, but it just shows, yeah, we can do that. We can train a set of archetypes using quantum annealing and optimization this way. And of course, what I think may be the most interesting aspect of using optimization to train a decision model is, of course, targeting a neural network. We've done some preliminary work on this, which I present here. Preliminary means that this on the left is the neural network that we actually managed to train. So 2 input neurons that work on binary input. It cannot do very much, as you can see. It still generates a rather large Cubo matrix due to overhead that is needed. So we have some theoretical idea on how this could be done, but any approach we've come up with so far just explodes within the translation to the Cubo problem, so that it's not really practical at all. So this doesn't also, as you can imagine, does not scale linearly. So if the work gets bigger, the Cubo matrix gets even bigger and much bigger, and we quickly lose any grasp of any practical meaning to this. But I think it's a good direction to look out for, because of course, training neural networks faster would be one of the killer applications that quantum computing could achieve right now, I think. All right, but this just is a bit of motivation. And what I also want to give you a little bit of, as you remember, for the classical approach, we've seen that a lot of classical hardware is also being developed to tackle this on the right here, the execution, and try to make this a little bit faster. And we also had some ideas into that direction. One of this, I think, is pretty straightforward. It's the problem of inference in Bayesian networks. So if we imagine a Bayesian network, it's probability network. I won't get into the details right now. It's a network of dependent probability variables, let's say it this way. And inference is just a question of, okay, I observe a certain variable. What is the most probable reason that I observe this variable? And we could translate this inference process as well into Cubo. So this is given that I already have a model like this Bayesian network, and I just want to use it in this way of inference. I can do this using optimization. Actually, we split this into 2 subproblems and then put it onto the quantum annealer. It fits quite nicely. Does not scale as nice, but it's okay for right now. So we have done some work on that. And much more recent, basically just last week recent, we came up with another approach that is targeting the game of life. This is probably also a well-known example in the computational sciences. It's a simple game played on a grid world with a few rules on when cells can get alive or dead, and alive cells are black in this depiction, and dead cells are white. And these very simple rules depend on the neighborhood, and we have some very simple dependencies. And we thought, hey, maybe we can not only optimize it, or you can just simulate it using a quantum annealer. I think this is very interesting because for us, it was an entirely new way to use a quantum annealer. And of course, we cannot fully simulate this. Game of life is Turing complete. Quantum annealing is not. But still, we could have some evolution of some variant of the game of life that actually ended up with some stability in the end, as you can see here. And what I found very nice is that the mapping to the cubo that we've seen here was very straightforward. So we just took the game of life grid and put it on the grid you've seen before, and just summed up some qubits that are connected already to represent one cell within the game of life. And then we could just use this edge weighting mechanism to simulate the game of life rules very directly. So for us, this was very inspiring. So far, it's not very useful because, of course, again, it's slower than if we would do it just on a classical machine. But it may point a direction on what I said earlier on how to use the noise of these quantum machines actually to your advantage. In this case, we wanted a probabilistic game of life, and we get the probabilistics just by the noise that's coming from a quantum annealer. All right. So as a quick outlook at the end, now that I've given a few pointers into how we could use these optimization techniques within quantum AI, I'd just like to ask the question, what's next? That maybe I accelerate a bit on the last part just to leave a little bit more room for questions and discussion. Basically, there are four major challenges I want you to take away from this that are the what's next in quantum annealing, at least from our perspective, of course. And the first one can again be derived, and it's probably the most important one, can be derived again from looking at this depiction we've seen quite a few times now today. And what I wanted to show here is that for all the quantum approaches that we found enhancing artificial intelligence, all of these are kind of anchored in one of these bubbles that try to improve one very specific step within this whole machine learning process. But of course, most of the time for a machine learning process is actually lost by repeating this inner loop lots and lots of times. And right now, this can only be done classically, as represented by the blue arrow. And that most of these approaches are built this way that we run the feedback loop classically, and then call quantum algorithms to do the subtasks at each specific point within the loop. What would be even greater, of course, is if we would find any way to shortcut this feedback loop. So we had this positional paper, we called this the holy grail of quantum artificial intelligence. This is what we're still working with. We have a classical feedback loop, and any way to shortcut it would be the biggest improvement we could possibly think of. But this is just the target we could keep in mind we could be heading for. This is a symbol I introduced for just shortcutting from the updates, from one update basically directly to the result, instead of iterating this loop over and over again. And so this I would like to call like the first and major challenge of quantum artificial intelligence. I don't know if it can be done. This I wouldn't promise anything on that matter, but I think from our thought process, you can see that it could clearly be the most beneficial improvement we could possibly get. So, and then for a few other challenges, as we've seen already in numerous slides within this talk, these representations of problems can become quite large. And as we know from gate-based quantum computing as well, large representations often mean lots of qubits, and lots of qubits often means not feasible on today's hardware. So eventually we need to find some way to compress data one way or the other, instead of just putting everything onto the machine at once to just handle the sheer amount of data. And this is kind of like the second challenge, just handle large amounts of training data using computers that are not really built for large amounts of process data right now. All right, the third challenge, and here I get to talk about Planck again. Again, you can see here the face of Frank Leimann, who already gave a talk a few weeks ago. He's the scientific director of the Planck project. And basically, it was him who noticed one particular problem with developing quantum algorithms at a large scale, especially if application domains are involved. And that is that you need a whole lot of knowledge. So you need a whole lot of people, and these people need to interact in meaningful ways, because right now, fresh from university, you don't get people who are experts in everything. You don't get an AI expert that also knows how to quantum compute, and maybe also knows how to implement the hardware, or how to apply the AI techniques to some domain. You don't get that at all. You don't get all of that at once in a single person. So you need teams and you need interfaces. And so within the Planck project, what we do is we define these interfaces and we define meaningful processes for these different expert teams to work together. So if interested in that, I think perhaps, yeah, keep an eye out for what we're gonna come up with. Planck is now just past the first year. We still have a lot to go, but we will provide some interesting solutions here to the general public. This is kind of the third challenge, providing the right interfaces on a software side, but also on a human side for different teams of different expertise. And lastly, this is kind of perhaps my bitter lesson from a few years of quantum computing, not a few decades yet. What we've noticed that there's one process in quantum computing that gets actually gets applied quite a lot. And I called it maybe the best quantum algorithm. And it works like that. You decide to go for a quantum algorithm for your company's problem, your company's optimization problem, let's say. And because you don't have the employees yet to do that, you employ a handful of specialists. You employ employ some people that are very good at algorithmics. You employ some people that are maybe very good at physics. They're very good with mathematical models, and you tell them to go look at your problem and come up with an algorithm. And chances are that the algorithm you're using right now to solve your problem was not developed by a team that was that highly qualified. But usually, as most software is written in the industry, that your algorithm, usually the algorithm used right now has been developed in dire need of a solution under more time pressure, under other pressures, more money pressure than what you're putting into your quantum algorithm right now. So chances are that your team of highly trained algorithmic people will come up with a better solution than the one you already have. The problem with this only is that the reason that this solution is then better may not actually be because of the quantum hardware you use. So for a scientist point of view, this is what you really need to watch out for, because actually we do not want to sell quantum algorithms that don't benefit from the quantum part at all. Or at least you want to be very cautious with that. And you want to point out, as I try to do with quantum annealing, that we're not 100% sure what's actually going on the physics side, and that this is not our expertise. We're just in the application. We can tell what's happening there. But I think we need to be very cautious where the benefit actually stems from, because of course, as quantum computing scientists, we are only interested in that solutions that bring a benefit because of quantum computing. On the other side of things, if I talk to industry partners about this, they're not worried at all, because they say, hey, we employ quantum computing specialists because we want to learn from the journey. And if they come up with a better algorithm that works for us, it's great. We don't care why it works. We're just happy that we've looked at it from a new perspective and came up with a better solution. So if you're practices, that may actually be a good thing. If you're a scientist, this is, I think, what you need to watch out for a lot when reading quantum computing papers. And of course, any meaningful way to easily pin down where some kind of advantage actually comes from would be helpful at all, would be helpful, really helpful in this case. But I'm not that hopeful that it's easy to come up with something like that. All right. So this would be like the 4 major challenges of things that are yet to do, or maybe will never be done, but could be worth aiming for. And with this, I want to conclude for today and say thank you very much for the attention. And yeah, I still have a lot of time for questions. We'll see how much time everyone else has.
Thank you very much, Thomas. That was really very interesting, at least to me, because I also work a little bit with this in this area. Not, I mean, my student works more than me, and I don't understand so much as she does. Unfortunately, she could not attend today, but we have some people here that want to ask some questions. I think I don't know if I start with Andre.
Hello, can you hear me?
Okay.
Yes, I hear you.
Yeah, oh, first of all, thank you very much for the very interesting presentation. I have a few quick questions. First of all, when you make a QUBO, with the constraints and the optimization
Yes.
parameters. You also have the Lagrange parameter, and I'm not going. I can imagine that's quite difficult or rather complex to explain it here, how to convert a machine learning problem to a QUBO. But one of my two questions was, how does in many machine learning algorithms and methods we have the hyperparameters? How much impact does a hyperparameter have on the formulation for a QUBO? On the QUBO formulation? And the second question is, have you thought or tried applying quantum machine learning to meta learning?
To what? Sorry, didn't get the last word.
Meta learning.
Meta learning. All right. So yeah, let's get into the first question, the translation. Well, of course, it depends on the algorithm we actually use. We try to come up with, usually, if I train a support vector machine, for example, the QUBO, if you look into the paper I recommended there, the QUBO is formulated in a way that the hyperparameters of support vector machines appear in the QUBO formula. So you just try to do it as general as possible. And then you can just compute. Of course, you want QUBO formulations that can train as many instances of support vector machine problems as possible. On the other side, of course, there are points where you just need approximations, where translating some machine learning problem one-to-one to QUBO is not feasible because of some overhead, of course, maybe you might need. And in these cases, you actually introduce additional hyperparameters. So I think what we noticed that because things like quantum annealing are on their own are very dependent on hyperparameter settings, and you don't get around to introducing at least these hyperparameter settings, oftentimes your translations on their own have additional hyperparameters. So overall, I'd actually say the hyperparameter problem is a bit worsened by this translation process. And I'd still consider it an open. Yeah, so you try to handle hyperparameters as you always do, make a good guess, make a few test trials. But I wouldn't say there's a clear-cut way on how to handle all these hyperparameters always in the best way. And for the second question with meta learning, I don't know of any approaches right now on the top of my head. What I've sketched a little bit, what we've seen is actually people applying machine learning to, for example, guess the hyperparameters for a quantum annealer. And of course, you can then always build a chain out of this, right? So if you have if I have a quantum annealer solving graph coloring problem, for example, and then I can train a machine learning model to actually guess the hyperparameters for the quantum annealer. And yeah, this lends itself to building kind of meta learning hierarchies. But again, I haven't seen any approach that actually integrates a stack, let's say, of meta learning. It's always just like the one-to-one translation that most algorithms are concerned about. But I think it's a very interesting aspect, especially if we want to think about ways that the feedback loop can be resolved. Then I think this integration of a whole stack of techniques is probably what we need to do. But I don't have any approach right now.
Okay, thank you.
Thank you. We have another question by Felix. It's about bibliography. And also Nahid wanted to say something as well. So Felix, do you want to pose your question, please? Felix? He wants to know what machine learning literature would you suggest someone coming from the quantum computing fields?
All right, so for the basics of machine learning, I mean, there's really a lot. There's this one book I can send some links if someone's interested in that. Of course, you can just mail me for additional resources. As a point to get into the things, of course, I'd be happy to recommend the paper we wrote. I just get back to it. There's this one paper that's very aggressively named It's just at the beginning of the talk. This one. It's very aggressively named the Holy Grail of Quantum Artificial Intelligence. It's more of a position paper, but it includes this overview. As this table is part of this paper. And we give a few links into literature as well here. So if you're, and a lot of this talk is taken out of it. So now if you've heard the talk, maybe you just want to look into the literature part of the paper. But here, I think we give a few interesting pointers. So I'd recommend this to get the pointers.
Okay, so we have a space. We are already running late, but I have some space for Nahid. Nahid wants to ask you some question.
Thank you. First of all, hello to all of you, and nice to hear from you. My question is, you talked about constraints. Do you mean state constraints? And it is the first question that I want to know. How do you consider this constraint? And the second is, you answered already my second question, but to know more, I want to know how the coherence is modeled in the algorithm or in the model that you consider.
All right. So first of all, for the concept, I think what you noticed is a kind of absurdity within my slides that I talk, of course, about QAR as the quadratic unconstrained binary optimization, and then we talk a lot about constraints. The thing here is that, yeah, QAR and is the problem basically that is solved by a quantum annealer, and it's inherently unconstrained. So everything if we have a problem with hard constraints, we can just make it a very strong soft constraint when we translate it to QAR. This is one of the things where I said translations usually introduce hyperparameters on how strong the hard constraints need to be after translation. But yeah, in theory, as you can say, we can express all two-way constraints. Every constraint between 2 qubits can be expressed this way. If we have constraints between 3 qubits, we need to build a workaround into this QAR translation. And this is the point where the QAR translation gets bigger, for example. So if I consider graph problems that are more connected than just pairs or something like that, then I always need overhead for more complicated constraints. So I don't know if this goes into the direction you wanted.
Okay, thank you.
All right. And for the second thing is, we are here right now in the very comfortable position that when we solve problems on the quantum annealer, we basically have 2 approaches. One is to use the actual quantum annealer, because while they're still a bit small for practical purposes, they are not that far off as quantum gate computers are right now. So I think the state-of-the-art D-Wave model offers kind of like 2000 qubits or a bit more right now. And as I said, you lose a lot of those because they are not fully connected, but you can still run at least some halfway interesting problems on that right now. So we can use the actual machine and not care about the decoherence model at all, because we just use what we get from the actual machine. Or the other way around, if we want to simulate the results, we usually don't go for a simulator at all. We just use a classical solver for this QAR formula, because it is such an easy mathematical formulation for combinatorial optimization. We can just use classical meta-heuristic search to search for QAR solutions without considering any quantum aspect at all. So this is what we do when we want to test, for example, our translations for very large instances. Then we won't consider the quantumness of the noise and just get any noise. And so far, actually, this has not trapped us anywhere. Of course, it's not entirely sound, because quantum noise may behave a little bit differently, but we haven't noticed any major instances of that.
Thank you very much.
Thank you.
Okay. It's running late. Before I say goodbye to everyone and thank Thomas, I would like to point out that we have the next talk coming on April the 7th. It's going to be given by Elias Combarro from University of Oviedo, Spain. So I put the link here in the chat for those of you that are here. I put the link for the QCTalks webpage. I would like to take the opportunity to thank very much Thomas for this that was very enlightening talk, at least to me, and I'm sure that all the audience liked it. I would like to also to thank to the audience to ask the questions and interact. These are being very nice, and it's been a very nice experience for all of us. Thank you very much, and see you next time. Thank you very much, Thomas.
Yes, thank you very much. I enjoyed it very much. Thank you for having me. Thank you for asking questions. See you next time.